you are going to integrate this twice, and the possibility of getting two unknown functions exists. So therefore you have to have two boundary conditions so that your final expression is devoid of any unknown function. And this integration would produce one more constant, but that constant this time would be function of x. That has to be remembered carefully, because you are now let's try and solve one more partial differential equation. The observation is very easy and simple. Here you are given two boundary conditions, because you are going to integrate this twice, and the possibility of getting two unknown functions exists. So therefore you have to have two boundary conditions so that your final expression is devoid of any unknown function. All functions are going to be defined for the final expression that you get for z. Z is of course the one that gives you the solution. The relationship between z and x and y, what you get is going to serve as the solution for this differential equation. And since there are two boundary conditions, that would ensure that both the integrations produce constants of integration, and both those constants of integration would be defined via these two boundary conditions. So if you integrate the given expression, the first thing that you get is the partial derivative of z with respect to y. Why? Because if you observe carefully, first it is differentiated with respect to y, then with respect to x. So your integration order would be in the same. So for just the reverse, first you are going to integrate with respect to x, subsequently with respect to y. So therefore what happens, you are going to get x square by 2, very simple integration here, because you are integrating with respect to x and keeping y constant, but the constant of integration would be that of y. Clear? So now let me make use of the first boundary condition to get rid of the first unknown function, rather transform that into a known function. So when I put y is equal to 1, I get x square by 2 plus f of y, and in the process I also change the definition of the partial derivative of z with respect to y, because when y is equal to 1, this is simply log x to the base e. So therefore my function f of y is now going to be defined as f of y is equal to log x to the base e minus x square by 2. Am I right? So this is the first value of f of y. So my partial derivative of z with respect to y, because I have already integrated with respect to x, right? So this is 1, and that is given by x square by 2y plus constant of integration f of y is now going to be log x to the base e minus x square by 2. Correct? So you can go back and confirm, yes indeed, that is the constant of integration, right? So therefore what we do is, next we are going to integrate with respect to y to get my final answer, but then also you would have one constant of integration, and the one that comes to our rescue would be the second criterion. Am I right? So if I integrate this with respect to y, you have to be very clearly familiar with all the fundamentals of integration. If you aren't, please visit our module on fundamentals of integration. 1 by y, if you integrate, remember always you are going to get log y to the base e. That's very important to note. Plus, if you are integrating these constants with respect to y, you are going to get y into those constants, that is log x to the base e minus x square by 2. And this integration would produce one more constant, but that constant this time would be function of x. That has to be remembered carefully, because your order of integration is with respect to y. So that is going to be, let us call that as h of x. Try to use symbolisms that are not used previously, so that you don't get into confusions. So now it is given that when y is equal to 1, this is going to go to 0. So what happens to the first term? Log 1 is always 0, whatever be the base. So therefore that simply goes to 0. Z is given to be 0 when y is equal to 1, and y here becomes 1, and then what happens? You get log x to the base e minus x square plus h of x is equal to 0. That means your HFS would simply be x square by 2 minus log x, right? So therefore, I can write it as h of x is simply equal to x square by 2 minus log x to the base e. Now there is no unknown function, both the functions are known. So let me rearrange everything. What is my final expression? Z is equal to, this is my final expression, x square by 2 into log y. So that is x square by 2 into log y plus, what is the next term? It is y into log x minus x square by 2. So that is y into log of x minus x square by 2. Whenever I write log x, please assume that it is to the base e, and then now h of x we just found here, it is nothing but x square by 2 minus log x. In fact, you can simplify this further, because you can take log x minus x square by 2 outside. So if I did that, y minus 1 I will get, because this is exactly negative of this. So therefore, if I take log x minus x square by 2 out, I will get 1 as coefficient of y, and this becomes minus 1. So that is where I get log x minus x square by 2 as the coefficient of that, plus x square by 2 log y. Right? So this is going to be my final expression for z. So let me explain again. So first, when I integrated this, going by the order, the latest differentiation is x, the first differentiation is y. So therefore, if I first integrate the function with respect to x, I get x by y, which is x square by 2y, and a function of f of y. Remember, you are integrating with respect to x. And once I get this, I want to redefine f of y, because I am given the boundary conditions. When y is equal to 1, the partial derivative of z with respect to y is log x. So therefore, I put y is equal to 1, replace the partial derivative by log x, and I get my value of f of y. Clear? This is step 1. Next, what I do, I use that in the actual expression, that is after integration. I have replaced my constant of integration by this term, and then I continue to integrate with respect to y. And you remember, x is kept constant, x square by 2 becomes a constant. 1 by y, if I integrate, I'll get log y. And then if I integrate any constant with respect to y, that constant into y. Because both these are functions of x, so both are constants, and constant into y, and plus one more constant of integration, that is h of x. Now, it is also given that z becomes 0 when y is equal to 1, right? Z becomes 0 when y is equal to 1. So therefore, what happens? I put z is equal to 0 and put y is equal to 1. And you note here that the moment I say y is equal to 1, log 1 becomes 0 and y becomes 1, and h of x becomes log x to the base e minus x square by minus, because h of x plus this function equal to 0. Obviously, when you take it to the other side, you get negative of this function. So therefore, what happens? You get h of x is equal to x square minus log x, because you got h of x plus log x minus x square by 2, 0. So I just brought it to the other side. So now h of x can be populated. F of y is also populated. So my expression is completely known. So therefore, I can simplify this by taking log x minus x square by 2 outside. When I did that, I get y into 1. And when I take this out, because this expression exactly is negative of this expression, so I get a minus 1. And then, of course, x square by 2 log y. And this is the final solution, which is devoid of any unknown function, right? So that was quite easy. All the skills that you require is that of integration and then simplification. Sometimes you may also get situations where you may have to remember integration by parts, but of course this was slightly a relatively easier situation. And also the boundary conditions can sometimes ask you to remember the value of trigonometric identities for various input angles. So let's move on and explore more varieties of situations. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.